convergent imagery. If you have a scene that you're collecting data from, and you're not providing any types of convergence there, the accuracy or the precision of these measurements is going to be impacted considerably. So you're going to be getting something, I put it in a bit more exaggerated, but this is from actual data that I've collected versus something that has convergent imagery. If you don't have that, you don't have the opportunity to get better results, particularly in the depth direction. So this is going to be the better one. The other one is the variation not only on the angle, but also on the height. So if you have, let's say, free, that you're trying to collect data from this point or this scene that is around X, one way is to have all of these images that you're collecting in the same plane, okay? But there's also another option to actually bring one of them at least, or some of them, with some variation of height. This way, you're not going to only have, let's say, convergence imagery in one plane, you're going to be having it in multiple planes. So a better result of this would be something like this, where the last one, you basically, or another one, or a few of them, you would actually have some variation in the height direction. What does this suggest? The more diversity we have in our measurements, the better it's going to be. Doesn't mean for absolutely every object or every scene this is going to be the case, but for the majority of the cases, the more diversity we have, the better the result is going to be. Why? Because that adds to redundancy, and that adds to the possibility of us being able to recover those unknown parameters. Okay? So this is going to be better. The other one is pre-calibration. It turns out that when I did some experiments on radius or diameter, if you provide the pre-calibrated, let's say, calibration parameters, it gives a better result. So that means that if you pre-calibrate it, and with calibrations that are target-based calibrations using best practices, you would get a slightly better result than if you just use the normal parameters that are provided by the EXIF, which basically CallMap uses directly. Video sequencing optimization. And this is what we talked about with respect to the data. So if the data basically goes around, what is going to happen? In this particular example, let's say you don't have, you move too fast. And in this particular situation, when you're moving too fast, you're also basically not changing your frequency by which you're decomposing your video into images. This is going to create some sort of inconsistencies here. There are two ways that you can improve this consistency, and that is by means of essentially having some sort of metric behind it. So for instance, if you have inertial navigation systems, you could actually use how fast you're moving in order for it to provide an indication of how frequent you're going to be reducing or keeping some of these images and decomposing that video. Or you can actually go inside of the features itself that is identified and see, dependent upon the features that you're observing for this image that can be capitalized as a whole, what percentage of it is actually used at the final structure from motion, or in terms of the, let's say, dense 3D reconstruction. And it turns out if it's not used enough, what it ends up happening is that it's not going to give you a strong network or a strong idea that this particular image is instrumental in this particular network. So the smaller this is, the less possibility you're going to be having as that particular image being utilized to its fullest potential in this particular network. What can you do then? You can increase the number of, let's say, frames just before or after this, dependent upon how this network overlap actually happens. So I give a definition of that, and then, so as an example, that first image was capitalized on 65% in terms of its main potential, because its potential is all of the features that it has. The amount of features that was capitalized in the 3D reconstruction is not as much. We want to make this as consistent as possible. That gives us a good indication, at least in this example or in my way of defining our network overlap, to be able to identify a better and more consistent network as a whole. And this is the example of 95%. So with the accuracy of that, 70, 80, 90, 95, if we enforce a network overlap that is 95%, the accuracy of the point measurements as a whole would actually improve quite a bit. And it turns out that if you use only the same points that are observed in the 70% and compare it, those same points or the closest points to those in terms of their accuracy actually improve more than the whole total points. In an actual lab, it's pretty consistent as well. So this was the results of the lab. This was the results of construction, more or less similar. But what this suggests is that if you have more overlap or you utilize these images to a higher percentage, the more possibility you're going to be having to getting a better accurate point cloud.